Okay, so the way how I like to create graphs in Python is, first of all, I'm going to create an object G, and then I'm going to do graph constructor. So I'm going to create a class of graph and then define a constructor. So double underscore init double underscore and then self. And in this self, or then in this constructor, we're going to initialize a member, and you do that by self dot member name. So we're going to call it the graph, and this is going to be an empty dictionary. And the reason why we do this is because we're going to be representing all of the edges and all of the vertices in this format, which is U followed by its key, which is going to be V1 vertex and W1 weight. And this is going to be a weight, this is going to be a list, and then V2 comma W2, and so on and so forth. So let's create an edge, and for that I'm going to do define add edge, and this is going to have a self, a U, a V, and a weight. And notice I'm writing add underscore edge, so please use this format because when I'm going to be displaying the graph, it's going to make my stuff or make my working very easy. Now I can do this in two ways. The first way is by doing if U is not in my graph, which is if U is not in my self.graph.keys, then what I want to do is create an empty list for my U. Whoops, there we go. And then I can create my connection, which is going to be U dot add, append B comma weight. Okay, and then I can do G dot add edge S to A with weight equals to 1. Let me create another one. Let's do this B, and let me print G dot graph. So you can see this works out. If I want to do this in one line, I can do this as self dot graph dot set default U comma. So I'm initializing U with an empty list if it doesn't exist, and then once that's done, I can append my V comma weight to it. Let's run this, and this also works. Okay, so for displaying my graph, I'm going to be using Networkx library. So first of all, I'm going to import these libraries, and I'm going to be importing my display. Okay, so these things, these functions, and how this is working, I'm going to explain afterwards in some other video, but I'm just explaining how I'm mapping my existing graph code to Networkx for just displaying the graph. So if you're using add edge, like you're using this format, right? What I'm gonna do is just copy this thing, and then I'm gonna paste this thing, fix the indent. So let's give this, okay. And then we're just going to change this method as nx.digraph, and you're done. And I'm going to display the graph. So g.display graph. And you can see it works. So that is how I like to create graphs in Python. Okay, so I've gone ahead and I have made some changes to the code. The first change that I've made is I've gone to this add underscore edge method, and I've just added this line of code. And what this does is it just initializes V as an empty list as well. So in the graph that I'm using, I've also changed like the display graph method, which is over here, and added more edges to it so that it's a bit more clear to see what the entire graph is doing. Similarly, I've done the same thing in the driver code as well, added more edges. And the reason why I've modified this self.graph.set default v comma empty list is because there was an edge case where C was just a leaf, and I wanted to make sure that there is also an empty list initialized as C as well. So now let's get towards to the point where we're actually discussing how we're going to be creating a function for BFS. So first we're going to look at how the BFS works, and then we're going to try to implement the BFS on our own. So the way how BFS works is by level-wise traversal. So first you're going to traverse S, then you're going to traverse to A and B, and then you're going to traverse to C, D, E, F, and then H, I, G. So it's similar to left to right traversals. Now for this, what we're going to do is we're going to use a variable called visited, and this is going to use a data structure. So this is variable name, and this is going to use a data structure of set. And for people who don't know what a set does, is set is just used so that for every value in your set data structure will be unique and it won't contain any duplicate values. So any list with only unique values is called a set, you can say, in short. And the next data structure that we're going to use is a queue. So queue is a FIFO data structure, which is first in, first out. And I just want to point this out that for a stack, whenever we are inserting any element, we're going to be using the terminologies push. And whenever we are deleting any element from the stack, we're using the terminology pop. And similarly for queue, it's NQ and DQ. So there might be times when I will be, I might accidentally say that whenever you're like removing an element from a queue, or I'm like popping an element from the queue, and that just means that I'm deleting an element from the queue. And whenever I'm saying push or NQ, just note that I'm talking about inserting an element into the queue. So now that we have established our base, now let's try to traverse the BFS ourselves. So the way how BFS works is that you're going to first of all put your first starting node into the queue. So the starting node S comes into the queue. Then we're going to check while the queue is not empty. What we want to do is we want to remove the first element from the queue, right? So we want to pop an element from the queue, so S is removed. And then we're going to put S into the visited. And then we're going to put all of the neighbors of S into the queue. So it's going to be A and B, and you're going to put A and B into the queue. Next, we're going to repeat while the queue is not empty. The queue is not empty because it has elements A and B. So you're going to remove A from the queue, put that into the visited, and put its child into the queue. So A's child is C and D. So you put C and then you put D. Now we're going to go to B. We're going to remove B from the queue, put B as visited, and then put B's children or its neighbors into the queue. So that's going to be E and then F. Right? And so on and so forth. So now let's try to code this out. Okay. So let me just create a function over here for BFS. So BFS is just going to be a starting node. So that's going to be an S. I need a start node. So first I need a self, I need a start node, an end node. Whoops, end node. And then what we need is a path. So we're going to be calculating the path as well. And we're going to be calculating the cost as well as to how much cost is it taking. And then comes our normal data structure. So visited as a set and a queue as a queue. Now, initially this will give you an error. So to import queue into the Python library, you're just going to use this part of code, which is from queue import queue. And once you just run this code out, you're going to get access to the queue library. Once we're done with this, we're first of all going to do what? We're going to put the starting node into the queue. So queue.put, and then we're going to put the start node into it. And then we're going to check, hey, while the queue is not empty, so while not queue.empty, what are we going to do? We're going to pop the first character off from the queue. So let's call it current node. And we're going to do queue.get. So queue.get is removing the first element from the queue and it's putting it into the current node. And then we're going to check, hey, if current node is actually the goal, so if my current node is actually the goal, I just want to return the path and the cost. And whenever we are fetching the current node, we also want to make sure to append it into the path as well, because this is also going to return you the path that was used. Also, yeah, okay. So the next thing that you're gonna do is you're gonna then check all of the neighbors of current node and put them into the queue. But before that, we need to first of all mark our initial node as visited. So visited dot add, and then we're just gonna mark current node as visited. Now comes neighbors. So put all of the neighbors of the current node. So put all of the neighbors for neighbors in my self.graph and current node. So this self.graph current node is going to return you all of the neighbors of which are connected to the current node, right? And I'm classifying them as neighbors. And for each of those neighbors, so I need to check if those neighbors are not in the visited set. So we're checking if the neighbors are not in the visited. So if they've not been previously visited, what I want to do is just put them into the queue. So queue dot put the neighbor into the queue. One thing that I have to do over here is that in the way how I've defined my graph is that it is defined as a node with a weight, right? So for that, I need to put my node and the weight as well. So this is going to return you two values. It's going to return you the node and it's going to return you the weight. And since we're also calculating the cost of the path as well, so I'm just going to add cost plus equals to the weight as well. And this should work, hopefully. And as you can see, it starts with S, then A, then goes to B, then C, D, E, F, and then I have H, I, and G. And the total cost of when you're going to accumulate all of those, you're going to get 24. Now, let's assume, so now you know how to actually like apply BFS, right? So from this point onwards, I'm going to now use Networkx library for BFS, DFS, and everything, okay? And the only difference is going to be some lines of code over here. So the only change is going to be made over here, and there's going to be a change made over here as well. Other than that, the entire code is going to remain the same. And let me just explain you what I'm inferring to. So what I'm saying is, instead of using the graph, creating a graph yourself, let's say that we created a graph using Networkx. So I'm going to unblur this and uncomment this, and I'm going to then remove all of this for now. And obviously this won't exist as well. So let me just run that. Okay, so what I've done is I've just you can say I've just like copied this entire function and just pasted it down here, and now this graph is behaving as a Networkx graph and not the graph that we created on our own. So this graph is created using Networkx and not our custom graph class that we just made. Now if I want to create a BFS function for this one, the way how we're going to do this is we're going to say define BFS. So this is going to need a start node, it's going to need an end node as we stated earlier, and instead of self, we're going to send an R node as an object to this function. So over here, I'm just going to write, hey, I'm going to apply BFS breadth first search on my starting node S with G and with my graph G. And then over here, this is going to return a path, this is going to return a cost. And now we are going to define our function. Now to define our BFS function, we're gonna do the same thing that we did earlier. So I'm just gonna copy all of this part, or in short, all of this part of the code, because this remains the same. And hopefully there are not indentation errors. And there are definitely indentation errors. Okay, I think this is all going to be, yeah. So now once we're done with this, now the only difference comes at the for loop part. So let me just write this down as well. Visibility.add current node, and then current node, and then let me add the change of the code, which is going to be for neighbors in my for neighbors in g.neighbors for current node. So this comes here, and you're going to check if neighbors not in visited, then what I want to do is just q dot, I think I made an error, spelling error. So I'm just going to copy this part, paste this here, and then just do cost plus equals to, now there are two ways to get the weight. The first method would be just getting g as current node. So from current node to my neighbors, and then add a weight over here. So this should work. And I'm not printing the path and cost, that's why I didn't get any results. So path comma cost, there we go. So S A B C D E F H I N G, and it's working. It's giving you a cost of 24. So you can do it either using this notation, or you could do it in another way, which is g dot get, I think this is get edge data. So g dot get edge data, and the data that we want is from current node comma the neighbors comma, okay, and the data that we want is going to be the weight. So weight. So these are the two different notations. So that was how you can create a BFS method using Networkx graph library, or using your own graph, custom graph library. Okay, so now let's create our GBFS function, and now from this moment onwards I will be just making functions using the Networkx graph library. And if you want to create the functions for your own graph, custom graph library that we just created, then you know how to do it and how you can refer it using this notation. But I won't be going into that. I will be just defining the GBFS and the UCS and Astar methods using the Networkx graph library. Now to create the GBFS method, so I'm going to write GBFS. And if you remember from my lectures, from my theory lectures, that GBFS works on heuristics. So I'm going to have a start node, an end node, a heuristic H, and it's going to also have the graph G. Now I'm also going to paste in the heuristics dictionary that I've gone ahead and I've created it beforehand, so it would save up some time. And let me just print something over here. So I don't want this red line. There we go. Okay, so just to give a very brief idea as to how GBFS works, is assuming that these are heuristic costs. Even though they're not heuristic costs, these are the path costs, but assuming that these are the heuristic cost. Oh my god, my laptop's gonna die. But assuming that these are the heuristic cost, and if you don't know what heuristic means, you can, again, I have posted a link down in the comments or in the description for the theory part of GBFS and informed search and uninformed searches, and you can go there and you can refer that. So the way how GBFS works is it chooses the minimum heuristic. So out of 3 and 2, we're gonna choose 2, and it's very similar to how BFS works in terms of code. Like I said, in terms of code, that instead of using a queue, you're just using a priority queue. So that's the only difference that's gonna be implemented in the code. And instead of a set, we can use a normal list, because then we can check for different paths and then check for the optimal path. So that's the only difference that's going to be made into the in the entire code. And if I want to dry run this, I'll dry run this for the first two levels. That is, first of all, you're going to have initial heuristic of S. Let's say the initial heuristic is 13. So it doesn't even matter, because initially you just have one option. So even if this heuristic is 0, even if this heuristic is 13, even if this heuristic is infinity, it doesn't matter to us, because we are going to put this S node into the queue anyways. So once we put the S node into the queue, then we're going to remove S from the priority queue, making sure if the queue is not empty, we're going to put it into the visited set. And then we're going to put S neighbors into the queue. So S neighbors is going to be A, and then it's going to be B. And now I have two options. If it was a BFS, we would first of all remove A and put A into the visited. But since this is a greedy best first search, therefore we will look at the minimum heuristic cost. And the minimum heuristic cost in this example, in the one that we're looking at right now, assuming that we're taking path cost as a heuristic cost, then it's going to be, we're going to choose B as the next visited node. So we're going to remove B from here, we're going to put P over here, and then put B's children into the queue. So that's going to be E and then F, and then goes the entire code. So the only difference is it's gonna be very similar to BFS, and the only difference is going to be importing a priority queue. So I've done that beforehand. Just call from queue import priority queue, and then you're gonna get access to your priority queue. So in GBFS, first of all, what we're gonna do, we're gonna create a path list, a visited list. I'm not going at the cost right now, because there are going to be some changes made to the cost functionality. Then what we need is going to be the queue. So I'm just going to call it a queue, and remember to call it like initialize it as a priority queue. And then what I'm gonna do is I am going to push the first element into the queue, which is going to be the start node. And the only difference in the code is going to be letting the code know which node has the least heuristic. So when I'm defining my GBFS function in the driver code, I'm just going to define it as GBFS. Then comes my starting node. So starting node. Then comes my graph G. Then comes my heuristic dictionary, which I've created over here. So heuristic dictionary. And then comes my my graph G. And right now I'm not implementing the cost, so I'm gonna remove the cost for now. And the way how we're gonna let the code know what the heuristic is, we're going to create double brackets for the queue function. So there's going to be double brackets inside here. And the first thing that we're going to pass in this method, or in this argument, is going to be h start node, comma, the start node. So now I am giving the heuristic of the start node as well as the node as well. So if I just print this queue dot queue, you will then see what this is doing is it's returning 13 comma s. Okay, so that's the only difference that we have to do. Then the entire method or the entire logic remains the same. So while the queue is not empty, so while not queue dot empty, we're going to set current node equals to queue dot get And this is going to return you two different values, so one for a current node, and we can say the other is the heuristic value, even though we are not going to use the heuristic value, but let's just initialize it to a variable q. And then we're going to create, are we going to create something? No, we're going to do path.append our current node, and we're going to check if our current node equals to our end node or not. If it is, then we just want to return the path, so return the path. And if that's not the case, then for each neighbors, so each neighbors in my what, in my g dot neighbors, I'm going to write current node. If neighbors doesn't exist, if my neighbors doesn't exist in the visited, so if the neighbors is not in visited, I am going to do what? I'm going to do q dot put, and in this put method we're just going to put the heuristic, so h of my neighbors, and then comma neighbors. So this one thing that I have to add over here is add the visited, so I need to append my visited as well, so append my visited as my current node, and now it should work, hopefully. Okay, it's returning me nothing. Why is it returning me nothing? Let's see. So I put this thing over here, I then return this. Let me just print this out. So print q dot current node. Let me see if I am actually getting it or not. Oops, I'm gonna get an error over here. Start node, end node, s and t heuristic dictionary. Okay. And let's see, print. Yeah, because I didn't add the function. Okay, let's try this now. Okay, there we go. So S and then B and then F and then G, and let me just show this to you, 1 second. So let me pull off the heuristic dictionary. So we start at S, which is at 13 over here. Then we have two options, A and B. I can also show you how it's actually deciding it. So I can print, wait, let me just do this over here. So print, let me call it a Q. And then over here, I think it's done like this. Q, no? I'll do it the standard way. So that's q.q, and then I'm gonna print. Should I print visited? I guess q would be enough. Okay, I'm getting an error. I cannot concatenate it. I think it's like f, and then it's something similar to that. I don't remember how I used to do that. So it's either, no, it's this, and then I think there's one over here as well. No, there's going to be this thing. I think that's how it's done. Q dot QUE. Yeah. Does that work? Okay, that works. So, okay. So initially I had 13. I had a decision of 13. Then I had a decision of 4 or 12. So I chose this one. Then I had a decision of 2. So S and then B. And then I have F, A, and E. And the minimum cost or the minimum dictionary, the minimum heuristic is 2 over here, so we chose F, and then G is 0, so we chose 0. So there we go. Now to calculate the cost. Now this is where it gets a little bit tricky. We were calculating the cost over here, because this was calculating the cost at each node, because when I went to S, then I want the cost over here, I want the cost over here, and so on and so forth. But this is not the case in GBFS. We just want the cost when we are actually going towards that path, right? So we want the cost in this cost method. We're going to be calculating the path cost, which is this cost. If I'm applying GBFS, so the answer to my GBFS is going to be S to B to F to G, and the cost to go from S to B to F to G is going to be 2 plus 1 plus 3. So we want an answer of 6. That's going to be the path cost. So to do that, we are first going to create another dictionary called cost, and we're going to initialize this to our start node and with a value of 0. Now in this method, or sorry, not the method, but in this chunk of code where I'm checking if neighbors not in visited, we're going to modify this a bit, and we're going to create a new variable called new cost and equate that to cost of my starting node. So sorry, cost of my current node. And the current node, once if this code is running for the first time, the current node over here is going to be our starting node with a value of 0. So cost of starting node is just 0 plus it's going to be the cost from my current node to my next node, which is my current which is going to be my neighbors, with the weight. So what I just did was, hey, my initial cost is 0. So let me just highlight this as to what I'm doing. So my current node is this thing. So current node is this thing with a cost of 0. And then what I'm doing is I'm adding that cost. So my new cost is this thing. So that's 0 plus the edge weight. And that's done using this thing, G current node. So current node is this part to my neighbor. So this whole part, and what I want from that G dot, the G current node to neighbors is its weight. So that's going to bring the 2 value over there. And my new cost is going to be new cost equals to 2. So that's what I've done. Now we're going to check one more condition, which is if neighbors is not in the cost, or if my neighbors, okay, I'm going to add this afterwards. So if neighbors is not in cost, what I want to do is I want to add the cost. So cost of my new neighbor as the new cost. So what this is doing is, hey, initially my dictionary just has start node and 0, right? And what I want to do is I want to add this new cost of 2 and set that over here, so that when I go to B and then from B to F, this already has accumulated cost of 2. So initially my cost dictionary had just start node, which was S. So it was just S with a value of 0. And once I've calculated this cost from S to B, I want to populate this by B as the new cost, which is 2. And then we're going to do this again for F. So F is then going to be 2 plus my edge weight, which is 1. So this is going to be 3. So this is what this line of code is doing. If the neighbors is not in the cost, then just add that cost to that cost dictionary. Now that once we're done with this part of the code, the next step is going to be to actually see what's happening. So we're going to return the cost with the end node. So we're just concerned with the cost of the end node, and we are just going to print the path and the cost as well. So this comes here, and the cost is 6. So we're getting the right answer. Now one change that I also made was this thing. I put this under this if condition, and it does make sense because we're always going to put the new neighbor, always going to put the new neighbor if it's not visited, and if it's not visited, then it will not be in the cost function. It won't be in the cost dictionary as well. Now, the last thing that I want to add is this might give you suboptimal answers. And to make this optimal, we can just add one more condition, that is um, if this is if neighbors is not in cost, or the new cost is lesser than my existing cost of neighbor. So this is just checking, hey, if I have, in this example, this wouldn't make a difference, but just to let you know that, let's say if I had S to B with a path of 2 and A to the path of A to B with a path of 1, then what this would do is, first of all, calculate S to B with a cost of 2, and then it would check from A to B, and A to B has a lesser cost than 1, so it's going to replace the cost of B as not to 2 but to 1. So this is just checking that if my new cost is lesser than the existing cost of that neighbor, then replace it. But like I said, in this part of code, this isn't needed, so this will also give you the answer. So that was GBFS. Do I want to put anything else in this? No, I think I've covered everything. Okay. Now that we're done with GBFS, we're going to take a look at how to implement the UCS. And the only difference in the entire code is going to be in that we're going to choose the next node on the basis of the minimum path cost and not the heuristic. So defining UCS is going to be a start node, an end node, and our graph G. Again, if you want to know how a UCS works, you can also look at my video on UCS. But anyways, I'm just going to copy most of the code from BFS because it's going to be the same. So BFS code is going to be the same thing, except for over here, we are going to then accumulate this using what? We're going to put our 0 comma start node, because the initial cost of the start node is going to be 0. And then over here, so current node dot get, this is going to return you two things, the cost and this thing. Then path dot append dot this, if current node double equals to this thing, visitor dot add current node, and we're definitely going to remove this thing, and we're gonna remove this, and we're gonna put, now this is going to return you the neighbors, and we need the weight of the neighbors, right? So the weight of the neighbors is going to be calculated. How is it going to be calculated? It's gonna be this neighbor, and I need the weight of that neighbor. What is going to be the weight? Wait, let me define UCS over here. So UCS, okay, yeah, of course, it's gonna give me an error. Yeah, of course, this is also going to be a priority queue. That was the difference I didn't encounter for. Now comes the part, so this is a priority queue, and yes, that's gonna give me an error because path dot append current node. Okay, let's create this as a list as well, and then I can do this as append. And the cost, what's going to be the cost? The cost is going to be how we have calculated this part, right, in GBFS. So just to repeat, we're gonna create a cost of so start node with 0, and then this is gonna return UC, and over here we're gonna check if the neighbors, so sorry, if new cost equals to my cost of my current node plus my from current node to my neighbors and visited, so sorry, my weight. Then what I want to do is if my neighbors is not, whoops, if my neighbors is not in is not in cost, or my new cost is lesser than my current neighbors. And in this example, this is important because you want to check the minimum cost. So this is very important. And what you want to do is set cost of the neighbors as the new cost. And then over here, we're just going to put our cost of the neighbors, comma this, and don't forget to add the double brackets. So adding the double brackets, putting an enter, running this, and I'm getting an error again. And the reason is because start node and node G, okay, too many to unpack because this is returning a cost as well. That's why. Okay, is it working? It's working. So let me go over here. I start with, okay, so this is returning the entire cost and I just need the end node part. Okay, now does it work? It works. Okay. So I started S. Okay, let me just try run this once very quickly to check if this is giving me the right answer or not. So I have, again, for checking how this works, I have made a tutorial on the theory part, so you can look over there as to how I'm calculating this, but I'm just gonna go do this as quickly as possible. So A, B, C, D, E, and F, and H, then I, and then G. So we have S, so from S to A we can go with a cost of 3, so 3 comma S, then I have a 2 comma S. Why am I doing this? Why am I doing this? I can just print the queue myself, right? So I don't have to check this on my own. Why am I implementing, why am I dry running it on my own when I can just do this thing? So this would be over here. Okay, there we go. So initially S to 0, I have B or A with a cost of 3, so I'm gonna choose what? I'm gonna choose B, right? And then I have 3, option of 3, 5, and E. If I'm choosing alphabetically or from left to right, I'm gonna choose A. Then I have F, D, C, and E. We're gonna choose F, right? Then I have D, because D is 4, so I'm gonna go S to B with 2, and then from here to here with a cost of 3, and then here with a cost of 3, and then this one is the cost of 4. Yeah, it is working correctly, which is the shortest distance from S to G is in fact 2, 1, and 3. Now we're gonna apply the Astar algorithm. So Astar algorithm is just a combination of GBFS and UCS. So I'm just going to copy this entire code again, go here, paste this down over here, and write this as Astar. And over here we're gonna add H, because H is going to be the heuristic dictionary, and we're going to add the heuristic dictionary. Okay, now over here the difference is going to be where it's going to be over here, definitely over here. So H is going to be, or I can say F, a function F is defined as H of my start node, so start node, plus my cost, which is initially 0. So I can do this, or I can just say cost of start node, and this will be better because when I'm going to go down there, it's going to help me. So this is just going to be F, and then everything remains the same. This could be like, I don't know, Astar something cost maybe. I actually don't need this variable at all. And over here, we are going to create F, just paste this over here and just do this as neighbors plus the cost of my neighbors, and this is now going to be f. Does that work? Okay, that is giving me an error. Okay, because UCS, this is gonna be what? Astar? Was that the spelling that I gave to my function? No. Yeah, it is. So I start with 13. Oh, it did give me the answer on the second try. Wow. Okay, let's try to dry run this, right? So S has a heuristic dictionary. S has a heuristic of 13. So 13, I'm just going to choose S initially. Then I have B, which is 2 plus my heuristic value, which is 4. So 2 plus 4 is 6. And my A is 12, I believe. So A is 12 plus 3, and that's going to be 15. So out of B and A, I'm going to choose B. Then I have the option of which one? F, A, and E, right? So F is going to be of cost, sorry, F, A, and E, right? Because B have a children, B have two neighbors, E and F. So F is 2 plus 1, 3. 3 plus 2 is 5. 5? Is it 5? 2 plus 1, that's 3. Yeah, 5. And then E has a cost of 3 plus 2, that is 5, plus the heuristic cost, which is 8. So 8 plus 5, 13. Yep, so it is working correctly. So that was BFS, GBFS, UCS, and Astar. Very, very similar. Now, finally, we're going to talk about how to implement DFS. Okay, now for DFS. I have decided that I've gotten a little bit lazy, and I will just explain how DFS is different from BFS, and I won't be writing the code as I go. Okay, so the difference is that it's pretty much the same thing that we have been doing with UCS, BFS, and GBFS, and the only difference is that now you're not going to be using a queue data structure, you're just going to use a stack data structure, and for calculating the cost, you're going to be using this method that we were discussing about, which was cost equals to star node, and you're checking that if the neighbors is not in visited, and then you're going to calculate the new cost, and if it is not in the cost, then you're going to calculate the cost. And the functions for stack are going to be stack.append and stack.pop. That's going to be the only difference, right? And everything remains the same. Now, if you're using this DFS functionality or this DFS method, so please note that your stack, normally when we're covering DFS, in theory, we're always talking about how it's moving from the leftmost side towards the rightmost, right? How is it moving from the leftmost depth to the rightmost depth, right? So it would first go from SAC, then it would go to D, and then it would go to BEH, and then it would go to FI, and then F to G. But when you're using this, if you're coding it in this way using a stack, then you're always going to start from the rightmost side. So as you can see, you have a S. Initially, you have S. You remove S. Then you put its neighbors into the stack, which is going to be A and B. Now from the rightmost side, you're going to remove B. Then from removing B, you will get E and F. Then in A and E and F, you're going to remove F. And then you get I and G, and then you're going to remove G, and then the algorithm finishes, and your path is going to be SBFG with a cost of 6, which was 2 plus 1 plus 3, which was 6. The other way how you could do this is by recursion. And that's also very simple. You're just going to write the parameters something like this, which is visited as none, path as none, and cost as 0. And you're going to say, hey, if the visit is none, which is initially going to be none, you're going to do visited equals to set. And then you're going to do if path is none, then you're going to set path equals to an empty list. And the difference is going to be, since you're not using any data structure, so this entire part of the code gets deleted, which is this thing, you're not checking if the stack is empty, you're not actually popping anything, and you're not actually pushing anything into the stack. So that all gets deleted. You're going to have an append, which is going to be over here, and visited is going to be pushed upwards above the function of above this part of the code, which is if current node equals to end node. So this gets pushed over here, then everything is same, and then you have everything is same. You're not actually adding the condition over here as if neighbors is not in cost and so on and so forth, because there's no cost dictionary used. And then what you're doing is you're just calculating result as DFS2 neighbors end node G visited path and new cost is calculated over here. And then this is going to keep on recursing. When it's going to meet your base condition, which is start node equals to end node, it's going to return a path and cost, which is going to be saved in your result. And you're going to check if my result 0, which is my path, is the node, is actually the end node, then just return the result, and this is going to return you the entire path. So in this functionality, you're going from left to right. So if I do this as this thing, you will see that I do in fact move from S to A to C, and then D, and then B, E, H, and then F, I, and G. But the way how I'm calculating the cost is just calculating through the shortest distance, the distance from S to G. So that was all from this part of the video, which was graph. Oh yeah, one more thing. In BFS, you will find that sometimes people are writing the visited not over here, but they're putting visited over here. And it doesn't really make a difference if you're putting a visit over here, which is you're checking if it's not visited, then you're adding it, instead of putting it over here. It doesn't make a difference, so you might find this change of code as well. Anyways, so this was all from this part of the video, which was coding for the graphs for DFS, BFS, GBFS, UCS, and Astar. In the next video, we will be talking about how to implement all of these different algorithms on mazes. So stay tuned for that, and yeah, see you later. Bye bye.